Okay, so before I forget, after this seminar, we'll take a picture just outside, so before the next talk. So we're now on the fourth seminar of the day. So André de Gouvêa is also a member of our scientific council, and he's from Northwestern University, and he, of course, is well known to the audience that works in neutrinos. So it's a pleasure to have him here.
Okay, so thanks a lot for the invitation. I have a cold, so my voice will be very strange. Hopefully it's going to last the whole talk. Otherwise, I'll just finish early and everybody will be happy. So I hope the sound is working fine, but we'll figure that out too. Okay, so my job is to tell you something about neutrinos, and in particular, I'll try to explain to you probably the most important question that people have been asking about neutrinos that we know has an answer. And so this is my job, is to tell you of something called the nature of the neutrino, which has to do with the possibility that neutrinos could be Majorana fermions. I apologize to condensed matter people in the room. This will be very confusing. Okay, so a very quick refresher. Neutrinos are fundamental particles, and they are the one fundamental particle where we learned something new in the last 20 years or so. So I'll just remind you very quickly of the stuff about neutrinos that you need to know to hear subsets of this talk. The most important thing is that neutrinos interact only via the weak interactions. That means that they talk to the W boson and the Z boson. And in particular, when it comes to the W boson couplings, we say that different neutrino species connect to different charged leptons. So the thing that's produced or destroyed together with the electron is called the electron neutrino. The thing which is produced or destroyed with the muon is called a muon neutrino. And the thing which is produced or destroyed with the tau lepton is the tau neutrino. And this is what we used to think about neutrinos by the end of the 20th century. So if you pick your favorite copy of Peskin and Schroeder, or some better particle physics book, then there would be some description of neutrinos, and it would say a lot of these things that are here. The thing which changed is the fact that we used to believe that neutrino masses were zero. And I'll try to highlight some of the features of that. It's one thing that people don't spend a lot of time thinking about, but massless fermions are weird. And we often don't think about massless fermions because when you're taking classes, you're normally talking about the electron all the time. But massless fermions have lots of interesting properties, including the fact that their helicity is a Lorentz invariant quantity. And this, of course, is a side effect of the fact that massless particles don't have a rest frame. And I'll talk about that in a little bit. And then, of course, the thing which is most important, which I'll talk about in lots of different ways, is the fact that if you look at experiment, we can make the following very absolute statement, which is every time we've done an experiment where a neutrino was involved, all of the neutrinos we ever produced were left-handed. That means they had left-handed helicity. And that's true every time we can measure the helicity, of course. And every time we produce an antineutrino, that antineutrino is purely right-handed. So the other thing which I will also talk about is that it turns out that neutrinos appear to obey a conservation law that we call lepton number. That means that if you assign the electron, the muon, and the tau, and the three neutrinos lepton number plus, and the antiparticles of lepton number minus, then for any physics process that you can think of, the total lepton number is conserved. So it's kind of like a conservation of charge, but it's a different charge called lepton number charge. The thing which, of course, is the big revolution that happened about 20 years ago is the fact that we've observed that these neutrino flavor eigenstates can be violated. That means that it's possible to produce a neutrino in a particular mass flavor eigenstate and detect a neutrino in a different flavor. So this is an established experimental fact. The only thing that's required for this phenomenon to happen is that you have to wait long enough. The consequence of this, and we're also very sure of that, is that it turns out that neutrinos have mass. So neutrinos have a non-trivial, non-zero mass. That's something we didn't know before, but it's something that we know now. So one could argue that that's a very interesting, very modern wrinkle in particle physics that we didn't anticipate 30 years ago. We can have a debate about whether people anticipated that or not, but we don't want to have that debate. So this is a picture of where we are. So we've discovered that neutrino masses are not zero, but there's something very exciting about neutrino masses, which is there's a bunch of other fermions which are fundamental particles as well, like the electron, the muon, the tau, and the quarks. And we know that they all have mass. And somehow we don't usually make a big deal out of that. On the other hand, I will try to make a big deal out of neutrino masses. So I want to try to explain to you why they could be qualitatively different. One way of thinking about this, and it's a very important thing to sort of take home, is the fact that if you plot these fermion masses and you plot their masses on the same plot, you have to do it in a log scale, which is already something that people have been curious about for a very long time. And one thing you might notice is that the charged fermion masses are very, very hierarchical. You know, they tend to be split by factors of 10, and they sort of span about 5 orders of magnitude. We don't know what that means. We don't know if it means anything, but it's something we've been worried about for a long time. Now, neutrino masses, it turns out, live here in this plot. We know for sure that neutrino masses are below an electron volt, and we don't know what the masses themselves are because our experiments can measure the differences of the masses squared, but they don't actually get to measure the masses themselves. So we have some degeneracy that we can't resolve with neutrino oscillation experiments. But the key point is that neutrino masses live here in this sub-electron volt regime, and if you were worried about this big gap here, you know, this is a much, much bigger gap. So the gap between the largest possible neutrino mass and the electron mass is bigger than, by about an order of magnitude, the gap between the electron mass and the top quark mass. And the other thing which is worthwhile pointing out is that, as far as we know, there are no fermions that live in between the neutrinos and the electron. And that's what the theorists worry about. We think that this is nature's way of telling us something we haven't figured out yet. So, of course, we've discovered that neutrino masses are not zero. The other thing that people will often tell you is that this is the first very simple evidence that we have that the simplest version of the standard model of particle physics is wrong. And what that means in a very simple way, because that's also a subject of a lot of debate, is that there are more degrees of freedom than we thought. They could be very mundane, simple, benign degrees of freedom, but we didn't know that they existed before, and now we believe that they exist. And what's exciting is the fact that we don't know what those degrees of freedom are. This is kind of a big deal for particle physics. If you work on particle physics, or if you have friends that work on particle physics, we're in the business of, if you want to oversimplify, finding out what's the physics beyond the standard model. And that's sort of an great business to be in, because the way we understand particle physics works ridiculously well. As far as all experiments are concerned, everything works, except a very small number of things. So here are those things. One is that neutrino masses are not zero. Then there's a bunch of other ones. The first one we're in the process of elucidating, and it looks like the standard model wins again, but that's not resolved yet. Everything else has something to do with cosmology and astrophysics. And it has to do with the fact that there seems to be something called dark matter, and we're very sure that dark matter has nothing to do with the standard model as we know it. Again, people try different things. The other thing is when you look at the universe, we can calculate, making some simple assumptions, how many baryons there should have been in the universe. And the answer is there's way too many, by about 10 orders of magnitude. So the universe did something wrong, and there are too many baryons in it. And there's something called baryogenesis, which requires some dynamics in the early universe that can only be explained by new degrees of freedom that are not in the standard model. And finally, the last thing is the fact that the universe has this bad habit of expanding too fast every once in a while. It's doing that now. It is very likely that it did that in the past, and we don't know how that works, but we're pretty sure that the standard model is agnostic about what the solution to this problem is. And this is the so-called dark energy problem, or cosmological constant problem, or the inflation problem. Okay, so let's talk about, yeah. I don't care about gravity. No, that is a, so he's saying that we don't understand how to include gravitational interactions in a quantum field theory. That's a correct statement. The vanilla particle physicist doesn't care about that because gravitational interactions at the particle level are completely unobservable, with some exceptions that people tend to get excited about. If you have theories of inflation, they can leave some imprints in the B mode spectrum, and I don't know anything about that. But you're absolutely correct. But the particle physicists don't care. I think you agree with that. There you go. So again, we need to give neutrinos mass, and we don't know how that happens. And it's not that it's very hard from a phenomenological point of view. The question you could ask is, can I write down a Lagrangian that obeys everything we know about the Standard Model, and the neutrinos end up with mass? The answer is yes. The problem in some sense is that we're very good at this. We can do this in lots of different ways, which are qualitatively different. And of course, we don't know what the right answer is. We don't think that nature does everything we think of, so nature probably chose one of these different ways of doing this, and we don't know what the right way is. And of course, in order to resolve this, we need more experimental input. I want to give you a sense of what this means in terms of things that you have heard about, either as a particle physicist or reading the general public stuff, because there are some younger students in the audience and some people that know nothing about particle physics. So we know that masses in the Standard Model are very strange. They come from this mechanism of symmetry breaking. And the neutrinos are not an exception. If you want to give the neutrinos a mass, that mass must have something to do with electroweak symmetry breaking. You can't violate that. However, what's interesting about the neutrinos is that they have choices that the other particles usually don't have. So here's a very broad description of what those choices are. So one possibility, so choice number one, is that maybe the neutrino mass is very similar to the electron mass or the top quark mass. It's a direct consequence of electroweak symmetry breaking. And the reason we don't often talk about this is because the neutrino mass is so small. And that's associated with what we call a coupling, and that coupling has to be very small, and we don't like very small couplings. If this is what's going on, you can actually make a prediction which is related to the stuff I'll try to explain, which is you predict that neutrinos are Dirac fermions. Another interesting possibility is that maybe there's another Higgs boson that we haven't seen yet, and maybe that Higgs boson only gives masses to neutrinos and not to anybody else. That's an attractive idea because it explains why the neutrino masses are very different from everybody else's mass, because they're talking to a different Higgs boson. There's a prediction here, which is that the neutrinos are Majorana fermions. For the experts in the audience, this model is very hard to make work, but just for the sake of full disclosure, but it's an idea, at least in principle. The third idea is very different. It basically says that neutrino masses are actually evidence of a new distance scale in physics. So we basically say that the neutrino mass is a combination of the Higgs mechanism and a completely different source of mass. So it's a much more complicated idea. And of course, that's the idea everybody likes. So if you ask your favorite theory friend, they will tell you that this is probably how neutrino masses happen. And then there's a consequence of this, which is that the neutrinos are also what are called Majorana fermions. So the way we're going to learn more about neutrinos is by getting lucky and by paying attention to lots of different things, because the information about the origin of neutrino masses can come from a variety of different places that go from cosmology to the Large Hadron Collider to searches for the mu-to-e conversion in nuclei, and everything in between. And the reason we don't know where the answer is going to come from is that we don't know where the neutrino masses come from. But one thing is we're very, very excited to understand whether the neutrinos are Dirac or Majorana fermions, and that's what I want to tell you about. Because if we found out what the answer was, we could at least eliminate half of the models, which is always nice, you know. So that's the idea. So again, this is the big question. Again, if you ask your particle theory friends, they will all tell you that if they had a genie that showed up and they could be granted one wish, it would be to learn if the neutrinos are Majorana fermions, because that would help a lot. We haven't found any genies yet, and the experimentalists are very slow, but we wait. So that's what I want to talk about. So the question is, are neutrinos Majorana fermions? And I will try to explain to you what the question means in a way that's very useful for what I'm talking about. And I want to remind you of how we understand the electron field, and I'll do this relatively slowly because this is probably the most useful part of this talk. So imagine that we didn't know about any particles, but we were doing experiments, and then one day we found out that there is such a thing as a left-handed electron. So you're doing an experiment, and there's a left helicity state, it has negative charge, so you're very happy, you discovered a new particle. With that discovery, you can instantaneously make the claim that there should be another particle called a right-handed positron. So if you believe in quantum field theories, those two particles are friends. They are related by the CPT theorem. So if you ever find an electron which is left-handed, then there must be a right-handed positron as well. If you keep doing experiments with your electron, one day you might find out that the electron has mass. So if you find out that the electron has mass, then you can also conclude instantaneously that there has to be a right-handed electron as well. This is not a very deep statement. This is related to the fact that if the electron has mass, you can go to the electron rest frame, and I'm just telling you that you can see an electron with spin up, and you can see an electron with spin down. Those 2 degrees of freedom exist. Okay, so that's the statement. If you don't believe me, you can sort of see the electron with spin up, and then you can turn upside down, and the spin will be down. So that's all. There's not much more than this. So of course, if this degree of freedom exists, then the left-handed positron, or the other spin component of the positron, has to exist as well. And this is meant to be very, very boring, but just to remind you of the fact that the electron has 4 degrees of freedom. So the electron field can destroy and create 4 different kinds of particles. And of course, I'm counting the different spin components as different particles. So we can do the same exercise with the neutrinos. Again, we know that left-handed neutrinos exist, so right-handed neutrinos must also exist. So again, the question that we're asking is, now that we know that the neutrinos have mass, we can go to the neutrino rest frame. So if you see a neutrino with spin up, you must be able to see a neutrino with a spin down. Now, this is where you have a choice. The reason you have a choice is you could invent a new degree of freedom, which is a right-handed neutrino degree of freedom, and you can have this be the Lorentz partner of the neutrino. They're related by a Lorentz transformation. On the other hand, the neutrinos are neutral. That's what makes them special. All the other particles have some charge. They all have electric charge, actually. So we notice that here's a left-handed neutral thing, and here's a right-handed neutral thing. So it is possible that the Lorentz partner of the neutrino is the same particle that you've already discovered before. Okay? So if the situation looks like this, then we say that the neutrino is a Dirac fermion. It contains 4 degrees of freedom at low energies. If the neutrino looks like this, then the neutrino has only 2 degrees of freedom. So if you ask, how many degrees of freedom do I need to describe a neutrino, the answer is either 4 or 2. So that's the question that we want to ask. We're basically asking whether this degree of freedom here exists as a Lorentz partner of the neutrino. Okay, so that's a hand-wavy description of what we're talking about. Now, you're allowed to ask, how come we don't know the answer to that? Because again, 4 and 2 are very different numbers. So if you can't tell 4 from 2, you haven't done very good experiments yet. And the problem is a technical problem, which is that the neutrino masses are very small. And what happens is the following. The only reason I could tell you that story is because the neutrino had a non-zero mass. If the neutrino had 0 mass, then whether or not this degree of freedom here exists is not a physics question, because it has no relationship to the neutrino. That means that you see a left-handed neutrino, you can't ask if a right-handed neutrino exists because the left-handed neutrino is always left-handed. You don't need a new degree of freedom if the mass is 0. So this is the challenge, is that if the neutrino mass had been 0, you would not be able to solve the problem of Dirac versus Majorana. And again, the way you want to think about this is that if you have a question that you can't ask, you can't answer either. So that's the important thing. And what happens in observables is that every time you construct an observable, that observable better fail in the limit where the neutrino mass goes to 0. So what happens in practice is the amplitude for any observable that can tell if the neutrino is Dirac or Majorana vanishes in the limit where the neutrino mass is 0. So that's the problem. So what's the hope? The reason that you have hope to actually answer this question is the fact that if the neutrino is a Majorana fermion, then from a quantum number perspective, there's no distinction between a left-handed neutrino and a right-handed antineutrino. Again, we don't even have to call that the antineutrino. We just call that out of habit. You know, if the neutrino were a Majorana fermion, there would be a left-handed neutrino thing and a right-handed neutrino thing. And we're in the habit of calling them neutrino and antineutrino because it helps our sanity in some sense. So anyway, so if this is the situation, then the neutrino and the antineutrino have the same quantum numbers. And in particular, if your particle-antiparticle pairs have the same quantum numbers, that means that they can't really have any of these quantum numbers. And in particular, they can't have charge, and they can't have any charge. So there cannot be a charge that you can assign to the neutrino. So that's the key point. And I try to mention very early on that the neutrino seems to have a charge, which is called lepton number. And that means that if the neutrino is a Majorana fermion, that better not be true. Okay, so that's the question. But of course, even if lepton number is violated, it doesn't have to be violated very much. It can be a really good approximate symmetry. And that seems to be where we are if the neutrino is a Majorana fermion. And I'm going to talk a little bit about neutrinoless double beta decay in a little bit. But let me give you an example of how this works, and hopefully this is useful for people that know something about particle physics. Let's say you're doing an experiment, and you have an electron hit something and produce a neutrino. Let's say you're doing this, so I will do this argument in the lab frame, but clearly you can make the argument in any reference frame that you like. The lab frame works better, but if you're perverse, you can do it in a different frame, and you should get the same answer. But you will be very confused if you try, so don't try. But this is the idea. If the energy is very high, because this is a weak interaction process, and I ask about the helicity structure of this neutrino, as you learned in the Dirac equation, this guy will be mostly left-handed with a very small contamination of a right helicity particle. And the contamination is associated with this small component in the Weyl basis, if that makes sense to you. So that's the way that you describe the helicity structure of your neutrino. Now let's say that my neutrino moves along and hits something. When it hits something, it will either behave like this state or it will behave like that state. When it behaves like this state, nothing exciting happens because that's mostly the weak interaction eigenstate. And that guy will mostly produce electrons. Life gets exciting when the neutrino chooses to manifest itself as the right-handed state. So when that happens, that's where the Majorana versus Dirac separation is very strong, because the right-handed helicity state in this reference frame where the energy is very high compared with the mass, that behaves mostly like the thing that we call the antineutrino. And what that means is when it hits something, it likes to produce a positron. What this means is you can do the following experiment. You can do electron producing a neutrino. That neutrino moves along, hits something, and has a probability of producing a positron. So I started out with one electron, and I ended up with one positron. So I violated lepton number by 2 units. Because I had one lepton here, I ended up with an anti-lepton on the other side. Of course, all the x's are different things, so just out of fun. Now, the catch is the probability that this will happen is, first of all, the neutrino has to be a Majorana fermion. Otherwise, this state here doesn't do anything. It doesn't interact. And the probability is proportional to this number squared. Okay? And if you plug in any reasonable numbers, so pick your favorite numbers, this is a really tiny number. So the probability that this will happen is a part in 10 to the 18. So it's very, very rare. Yeah? It's impossible. The way that we do the experiment is by taking advantage of nuclear physics, which is what I'll talk about next. So instead of trying to do an experiment in a collider-like environment, you can do it in the virtual world by doing nuclear physics. The reason for this is easy to understand. You know, nuclei are cheap. You can get a lot of them. And if they're decaying, you just have to wait long enough. So it's a much better experiment than throwing things at a wall and waiting for something exciting to happen. So that's the summary of why we go and talk to nuclear physicists. And the idea is the following. And I'm not going to talk about this too much, but people can ask me. There's this thing called double beta decay. It's a very rare nuclear physics process where you have a nucleus that for some reason cannot undergo beta decay, but it can actually undergo 2 beta decays at the same time. So it's a process where a nucleus converts into a nucleus where the Z number changes by 2 instantaneously. And then in that process, you emit 2 electrons and 2 antineutrinos. That's double beta decay. That's been observed. These are probably the longest lifetime processes ever measured, period. The numbers are like 10 to the 25 years. I'm making this up, but it's approximately right. So if you look it up, I'll be wrong by a few orders of magnitude. So what we look for is a variant of this process where a nucleus decays into another nucleus and emits 2 electrons and nothing else. So if you want to think about it in terms of Feynman diagrams, it's a process where complicated stuff happens. 2 virtual W bosons come in, they exchange a neutrino, and then they turn into 2 electrons. And this can only happen if the neutrino is a Majorana fermion. Because you notice that I had no lepton number in the beginning, and I have a non-zero lepton number in the end. What's exciting is we can estimate the size of this diagram, which turns out to be proportional to the neutrino mass. And we can say, okay, so if this is the dominant contribution to neutrinoless double beta decay, I can estimate what the rate should be. So if somebody does an experiment, they can check if my prediction is correct or not. And the prediction depends on the neutrino mass. And these are what the predictions kind of look like in terms of some effective mass, which is not important. The effective mass is what the experiments measure. And the idea is that the experiments are, this figure is old. The experiments are around here now. And people are building experiments that get here. And then you notice that you start to rule out regions of your parameter space in a non-trivial way. So we, meaning the nuclear physics community in the US, and a big chunk of the particle physics community in Europe and in Asia as well, have been spending a lot of resources looking for this neutrinoless double beta decay process. So it's a very difficult thing to do in practice because you're looking for this process and you have the ordinary double beta decay on top of this. So you have to be able to separate them out. Kinematics helps, but it only goes so far. So it's a big activity. And again, the name of the game is to ask if lepton number is violated. If lepton number is violated, we conclude that the neutrinos are Majorana. If you don't see anything in this experiment, you don't conclude anything. That's the downside of having a negative result in an experiment. You know, you can't prove that something didn't happen. You can prove that it doesn't happen with a certain rate. But if we make a lot of progress for the next decade, we hope to be able to get to a point that if we don't see anything, we'll start suspecting that the neutrino is actually a Dirac fermion. Okay, so again, let me remind you of why this is so difficult. It's the same idea, right? You know, so the neutrinos that we produce are mostly left-handed with a small contamination of the right-handed part. The right-handed part, in many quotes, is the thing that has the power to tell you if it is possible to have a neutrino that behaves like the thing that we normally call the antineutrino. And again, this becomes very difficult because the neutrino mass is very small. Now, if you're a physics student and somebody tells you that something is very small, you should tell them that that's a meaningless statement because there's no such thing as big and small. There's just big and small relative to something. Unless you work on quantum gravity, and then your relative something is equal to 1, and then things which are very small are much less than 1. But again, what we're talking about is the fact that this is very difficult because whenever we do an experiment, the typical neutrino energies are way bigger than the neutrino mass. So that's what very small means. So again, how do we resolve this issue? How do we make life easy for us? And like I said, there are basically two ways. The one that I told you about a little bit is the fact that you can find something that only Majorana neutrinos know how to do. And I told you that they know how to violate lepton number. So you can look for that. The other thing you can do is that you can, what if you didn't have to work with these ultra-relativistic neutrinos? Why don't we just choose to work with slow neutrinos that don't move very fast? Then life is much easier. Then there's very little confusion between Majorana and Dirac. So that's what I'll try to tell you a little bit about. And I'll say right away why this is very hard. So again, I'm going to discuss a couple of examples of circumstances where we believe that we can find some slow neutrinos. One way, of course, is that they actually exist and there's a whole bunch of them. There's this thing called the cosmic neutrino background. We're very sure it exists. And the neutrinos are moving super slow. And they're right here in this room in very large numbers. So that's one good source that's free. Another possibility, of course, is that you can do a very low energy reaction where you can produce a non-relativistic neutrino in the final state. So that looks like a good idea. And then the last thing I'll say something about if I have time is, it turns out that if you could measure neutrino decay, it would reveal whether it's Majorana or Dirac in a very simple way. Actually, it does that in a variety of ways. And I want to highlight a super simple way of doing that. Now, why don't we ever work with non-relativistic neutrinos? One reason is that we don't know how to produce them. Most physics processes are, nuclear physics processes where the energy is automatically MeV. So you don't have a choice. You can't not work with MeV energies. You can try hard, and then maybe they get to keV. But that's still a factor of 10,000 too big. So the other problem, of course, which is the real problem, just as a reminder for people that don't think about particle physics, is that the neutrinos only interact via the weak interactions. And as you might remember, the weak interactions are very weak, which is why they're called the weak interactions. And that's especially true at very low energies. So the cross-section kind of grows with the energy, or worse. That means that as you go to low energies, the cross-section is nothing, which is the real problem. So you have to be very good at doing experiments. So on the other hand, the problem that we're trying to solve is an easy problem in terms of the differences between the two kinds of neutrinos. It's just that you don't have any rate, but that's a different problem. So let me say something about the cosmic neutrino background. I assume you've all heard about this before. There is this cosmic neutrino background. The average temperature is about 2 Kelvin, which is about 10 to the minus 4 electron volts. And 2 of the neutrino masses are bigger than that. That means that at least 2 neutrino species are non-relativistic on average today in this room. So that's great. So the key thing is that it turns out that if you try to think about this cosmic neutrino background, probably the best way to think about it is to say to zeroth order, this is a neutrino at rest. Locally, it's probably polarized. It's described as a spin up in some direction. And what happens is if you try to hit a neutrino at rest, whether or not the neutrino is Dirac or Majorana is qualitatively different. Because if you hit a neutrino at rest, you're either going to, and you're working with the weak interactions, that's the key point. You're either going to talk to it via a left chiral current or a right chiral current. It turns out that if the neutrino is Dirac, there's no right chiral current. The right component of your neutrino doesn't interact. So that means when you try to hit a neutrino at rest, half of the time nothing happens with the weak interactions. When you hit a Majorana neutrino, half of the time it's the same as the Dirac neutrino. The other half of the time, it behaves like the antineutrino. So it basically means that you get to hit the neutrino in two different ways. If the neutrino is Majorana, and if the neutrino is Dirac, there's only one choice, because there's no right-handed current. In the case of the Majorana fermion, the Hermitian conjugate of your current is also operational with your particle. So that's the plan. For the cosmic neutrino background, the story is very similar, because you have to remember that the cosmic neutrino background has both, in quotes, the neutrino part and the antineutrino part. So if you do an experiment like this, for example, where the neutrino hits something and turns into an electron, if I'm a Dirac neutrino, I only get to talk to the neutrino part of my cosmic neutrino background. And if I'm a Majorana neutrino, I have a chance to speak both with, in quotes, neutrino part and the antineutrino part. What that means is if I do an experiment where I can measure this cosmic neutrino background, the rate between Dirac and Majorana will be different by about a factor of 2, which is a huge factor. I mean, it's a big factor. That means if you can see 10 of those, you can distinguish it at a very high confidence level. So that's very exciting. That was pointed out in this paper, which is here again. Now, why aren't we super excited about this? The problem is we've never seen this cosmic neutrino background, period. Not even one event. So 10 is farther away. The other problem, of course, is that we don't actually get to measure the cross-section. We measure the flux times cross-section. So the question becomes, how well do you know the flux here? And the answer depends on who you ask. I think chances are that you probably get to know this flux reasonably well, but for perverse people, they can tell you that the neutrino flux here can change by, I don't know, a factor of 2. And again, that's not what I want to talk about, but that's the other challenge, is that if you believe that you don't know the neutrino flux very well, then you're stuck. Okay, so I want to mention two things very quickly before I stop. One thing that we looked at just for fun is we did a calculation. So let's do E gamma goes to E nu nu bar. That's an experiment I know how to do. I know how to produce photons. There's a lot of electrons. I do the experiment. The observable is an electron and nothing else. And of course, I can do this at super low energies. You know, I can buy a flashlight and the energy is super low. So that's the idea. And then what happens is I can do the calculation, and I can do it for different neutrino masses. And there's some diagrams. You can do the calculation. It's fun. It's easy. And here is the matrix element squared for different final states. So these are the neutrino mass eigenstates. And this is the matrix element squared. And what I want to highlight is that if you look at this, this is a log scale. This is as a function of the photon energy. So when the energy is very small, that means that the neutrinos that you're producing are non-relativistic. And you notice that the cross-section is different by a factor of 2, just about, if the neutrino is Majorana or Dirac. The way that you can understand this is that if the neutrino is Majorana, there are more diagrams that interfere with one another. And if the neutrino is Dirac, that's not the case. That has a big impact on the rate. So that's the good news. The other thing that you see is that as the photon energy gets bigger, then the neutrinos start to become relativistic, so the difference goes to 0, which is what you expect. Okay, so that's the good news. The bad news is that you can't read these numbers, and that's on purpose, but these numbers are really small. So even though the difference is really big, the cross-section is really small. And if you actually wanted to do this experiment, it would be completely hopeless, because it has like a background. You know, imagine that you're doing gamma E to gamma E, where the gamma comes out with very little energy. And you can say, oh, maybe that doesn't happen, but I can do the gamma E to gamma, 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 gamma E, and then all these photons have very little energy. And the cross-section for that is way bigger than the cross-section for this. Not to say that we estimated what kind of powers you needed, and it was kind of laughable. So anyway, that's the idea. So I'm going to skip this, and I want to say something about neutrino decay, and then I'll stop. So the other thing you can study is neutrino decay. What's interesting about decay is that, in some sense, the decaying neutrino is always not relativistic, even if it looks relativistic in the lab frame. somehow when the neutrino decays, it is telling you what its reference frame is. So it's giving you some information that you can take advantage of. Now you can say that you've never heard about neutrino decay. And I will just remind you that in the standard model, the neutrino decays once you assume that the neutrino mass is not zero. That does not depend on how you give the neutrinos a mass. If you only assume the weak interactions and massive neutrinos of any type, Dirac or Majorana, and you don't know how the mass has happened, there are two decays which are guaranteed. The heavy neutrino can go into a lighter one plus a photon, or the heavy neutrino can go into 3 of the lighter ones. If you never thought about this, you conserve everything. Angular momentum is conserved, energy is conserved. If it's allowed, it's mandatory. So you've all heard this before. So that means that only the lightest neutrino is stable. Of course, you can calculate the rates in the standard model, and the rates are sort of ridiculous. You know, again, the width goes like the neutrino mass to some power. The neutrino mass is very small. If you plug in numbers, the lifetime is like 10 to the 40 years. So not too many neutrinos have decayed yet. Nonetheless, let's ask what happens if the neutrino could decay. So we did a fun exercise, which is, let's say that a heavy neutrino decays into a lighter one plus something else, let's say a photon. We can calculate what the angular distribution of this photon will be. And very generically, that angular distribution goes like something 1 plus some number times cosine of theta. That asymmetry parameter alpha depends on the interaction. So if the neutrino is Dirac, I can do the same calculation for the antineutrino. And that decay goes like 1 minus alpha cosine of theta. This is a very generic result. It's a leading order result if you assume CPT is conserved. It's an exact result if CP is not violated. If CP is violated, there are higher order corrections to this. But the key point is that those two numbers are actually the same. And remember, there's a plus and minus sign here. If the neutrino is Majorana, what you measure, if you measure the angular distribution of this X particle, which maybe is a photon, you actually measure the sum of these two things. That means that regardless of the physics that describes neutrino decay, if the neutrino is a Majorana fermion and it decays in this two-body way, the decay distribution is isotropic. This does not depend on anything. It's a property of the Majorana fermion. If it's not a Majorana fermion, if it's a Dirac fermion, it can be whatever you want. It depends on the nature of the interaction. It could be 0, which would be unfortunate, but it's in general not 0. So we looked at this, and I'm not going to talk about that. We did do a calculation of what's called a neutral heavy lepton. This is something that people like to study. So they say, imagine there's a new neutrino that's heavy. Where can we find that? And there's different places, you know, the Large Hadron Collider, meson facilities, you know, neutrino scattering experiments, and so on and so forth. And if you calculate these decay parameters, depending on the mass, depending on the other particle that you're decaying into, this decay asymmetry can be very large. So that's generically what you expect. So you normally get something that allows you to tell if you see a decaying neutrino and you know the physics that describes neutrino decay, you can tell Majorana from Dirac, which is kind of cool. On the other hand, we don't know if these neutral heavy leptons exist. But that's a detail. We worry about those things later. Okay. So I think my time is up, plus or minus 1 minute. So let me just quickly summarize. So again, Majorana fermions in particle physics and Dirac fermions in particle physics are qualitatively different things. They even contain different numbers of degrees of freedom. For the neutrino, which could be a Majorana fermion, asking whether it's Majorana or Dirac is very difficult because you can only solve this question if the mass is not 0. For a massless fermion, being Majorana or Dirac is a non-question. So that's the challenge. The neutrino mass is very small. So every time you do an experiment, you have to fight that. So the ways around it that we have is we either have to look for something that the neutrino can do only if it's one type of fermion or the other type of fermion. And that's where we're investing a lot of money. So we want to be able to see if lepton number symmetry is violated. And if it is violated, again, independent of the physics that describes lepton number violation, the neutrino would be a Majorana fermion. The other idea, which people are starting to think about a little bit more, is that the other way to see if the neutrino is Majorana or Dirac is to work under circumstances where the distinction is very large, which is what happens when the masses are very small. This is experimentally very challenging, but there are some avenues that one could pursue, and this is what we've been looking forward to. So I'll stop here. Thanks.
Could some neutrinos be Majorana and others be Dirac?
That's a good question. Given everything that we know about the standard model neutrinos, no, because they all mix. So you have an interaction where all the mass eigenstates participate in the same interactions. So I think the answer is no. We've asked ourselves that question many times, and we land at different places, but I'm pretty sure the answer is no.
So I had the impression you were going to talk a little bit more about the possibility of the neutrinos not having mass. Is this completely ruled out?
I'm sorry, yeah, so good. So what I didn't do, but I promised is...
yes.
So we know the neutrino masses are not zero. So from a factual point of view,
Okay.
the neutrino masses are not zero. At least 2 of the 3 masses are not zero. Now,
Why?
that's an experimental fact.
Okay.
We don't know how, but we know that that's true.
Okay.
What I wanted to say is that if you do have a massless fermion has this absolute helicity conservation. And a massless fermion is such that you can't ask if that fermion is a Majorana fermion or a Dirac fermion. It's a non-question. It's a non-physics question.
Okay.
This is a useful thing to do calculations, by the way. When you do calculations at a collider environment and you work with electrons, the electrons are not massless, but they almost are. You know, the mass is super small. So you can develop a lot of intuition by pretending that the electron mass is 0. And if you do that, you can treat the left-handed electron and the right-handed electron as different particles. They don't know about each other. They're just different fermions that have no connection to one another. And that's a good way of understanding a lot of details of scattering, for example, at very high energies. So I think that's what I meant.
Okay. Thank you.
The question?
So at the beginning of your talk, you said that one way to give mass to neutrinos would be to couple them with the usual Higgs field, right? Except for the fact that these couples would have to be really, really small, does this mechanism lead to any problems?
No, not at all.
So
The only thing that's exciting, so there are 2 things which are exciting about this. One is that you have to add a new degree of freedom. The right-handed neutrino degree of freedom, as far as we know, doesn't exist. So until you do an experiment that proves that that degree of freedom exists, you should be skeptical. So you have to add a new degree of freedom. There's one issue which is a little bit more technical, which is the following. So I talked about lepton number for a long time. If you talk to particle physics people, we're very skeptical about whether lepton number is a conserved symmetry or not. We think it shouldn't be, because lepton number is what's called an accidental symmetry. It is not a symmetry that you asked for. It's just a consequence of all the quantum numbers of all the particles. So it's a quantum number that you got for free. What that means is that if you add any new particles to your model, it's more likely than not that lepton number will be broken. Now, if the neutrino turns out to be a Dirac fermion, then you will have missed an opportunity to break lepton number. A big opportunity, because this right-handed neutrino degree of freedom can violate lepton number for free. You just add it to your Lagrangian with a huge parameter in it. So you have to explain what that means, and explain is always a difficult word. But what it means is that then lepton number now is a good symmetry of your Lagrangian that you have to impose. It doesn't come for free anymore. Is that somehow if the neutrino is a Dirac fermion, then lepton number is a fundamental symmetry of nature. If you ask our quantum gravity friends, They say that that can't be true because global symmetries are broken by quantum gravity effects. I think that statement is true, but you can correct me, and I'm sure there's a lot of asterisks that you can add. So that's the challenge. You know, we would learn something about this lepton number symmetry that would change the way that we look at it. You know, we look at it as a cheap accidental symmetry that's probably broken, and we would have to change it into something that's part of any fundamental symmetry that you write down. And that's a big change, at least for the theorists, you know.
Other questions?
Let me return to this former question whether why it cannot be that there exist simultaneously Dirac and Majorana neutrinos. I'm not claiming that some of them are of one kind and others of another, but both the electron mu and tau neutrinos can exist in both states, and we can observe the mixing only of the Dirac neutrinos, but not of the Majorana ones. Is it a possibility, or it is also ruled out?
So that's, there are different statements, and the safest statement that we like to make, which is less confusing, is to never talk about electron muon and tau neutrinos. Talk about the mass eigenstates. You know, the mass eigenstates are the things that have a Dirac equation, are the things that you can quantize. And what the mixing is telling us is that these, all of these mass eigenstates share all of the interactions with the electron, the muon, and the tau. So that's why it is very difficult to construct a scenario where you don't add many more degrees of freedom, where you have one of these states being a Dirac fermion, the other one being a Majorana fermion. So that's one part of the answer. As far as the mixing is concerned, the mixing experiments cannot tell if the neutrino is Majorana or Dirac. And that's why we don't know the answer, because if we knew that, if we knew, for example, that only Dirac neutrinos can mix, then we would know that the neutrinos are Dirac. So from the mixing, from the oscillation perspective, Dirac neutrinos and Majorana neutrinos are effectively the same. And that's a side effect of the same physics, which is the neutrino energies are very high. So any effect which would tell you if the neutrino is Majorana or Dirac is very, very suppressed. And that's also true for an oscillation experiment. So I don't know if that answers the question, but basically that's the challenge is that you have three mass eigenstates. They all couple to all of the different charged leptons and the W boson. And that makes some of them being Dirac and some of them being Majorana a very difficult thing to do technically. So that's one way of thinking about that. You know, the hand-wavy way is to say that, you know, if the nu E can oscillate into a nu mu, and the nu E is a combination of 1, 2, 3, and the nu mu is a different combination of 1, 2, 3, how can some of them be Dirac and some of them be Majorana? So that's the challenge. That's a different way of thinking about that. So I don't know if that answered the question.
I want to ask, I don't know if it's a silly question, but is there any third theory besides Majorana or Dirac?
So in the realm of particle physics, which is very boring, no. If you work on solid-state systems, where they have all kinds of weird fermions and they have parastatistics and weird things, then you get all kinds of different, in quotes, fermions or things in between. And that's because they cheat, right? I mean, they can produce these things in the laboratory. And they get all kinds of weird equations that describe these would-be fermions, for example. But in particle physics, these are the only choices.
Okay, so if there are no more questions, let's thank André again. So can everybody just leave the auditorium, just stand just outside there, and we'll take a picture, and then you can go back in the auditorium.